the fast train that isn't. It accelerates smoothly out of Boston's Back Bay station, its streamlined nose designed to slice through the air at speeds that would make most American trains seem antiquated. The Acela Express, Amtrak's flagship, America's answer to the bullet trains of Japan and the TGV of France. With its tilting technology borrowed from European high-speed systems and its premium business class interiors, Acela represents the pinnacle of American passenger rail. It's the train that businessmen and politicians choose when they need to move between Washington, New York, and Boston. It's the train that's supposed to prove America can compete in the world of high-speed rail. But here's the paradox that defines the Acela story. Despite its futuristic design, despite the marketing that calls it America's high-speed train, Acela has a maximum operating speed of just 150 miles per hour. And it only reaches that speed on a few short stretches of track in Rhode Island and Massachusetts. For most of its journey along the 457-mile Northeast Corridor, Acela travels at speeds that would have been unremarkable to the streamliners of the 1930s. Compare this to Japan's Shinkansen, which routinely operates at 200 miles per hour, or France's TGV, which holds the world record at over 350 miles per hour and maintains commercial speeds of 200 miles per hour as a matter of routine. Even Spain, a relative latecomer to high-speed rail, operates trains faster than America's flagship service. So, what happened? How did the country that pioneered so much of modern transportation technology end up with a high-speed train that isn't quite high speed? The answer to that question takes us back more than half a century, to a time when American passenger rail was dying, and the rest of the world was racing ahead. The origins. How the U.S. lost its speed. To understand Acela, we need to understand what came before it, and that means going back to a time when American passenger rail wasn't struggling, it was thriving. In the 1920s and 30s, passenger trains were the primary means of long-distance travel in America. Railroads competed fiercely for passengers, introducing streamlined trains with names that still echo through railroad history. The Super Chief, the 20th Century Limited, the Broadway Limited. These weren't just trains, they were institutions, symbols of speed and luxury that connected America's great cities. The Pennsylvania Railroad's Metroliner service between New York and Washington offered electric multiple-unit trains that could reach 160 miles per hour in testing. In regular service, they achieved speeds competitive with anything in Europe at the time. American passenger rail was world-class. But then came the changes that would reshape American transportation forever. The Federal Aid Highway Act of 1956 committed the nation to building 41,000 miles of interstate highways. The jet age arrived, making long-distance air travel practical and increasingly affordable. And perhaps most significantly, Americans fell in love with the automobile in a way that no other nation quite matched. For the railroads already struggling with the high costs of maintaining passenger service, this was catastrophic. One by one, the great-name trains disappeared from the timetables. The Pennsylvania Railroad and the New York Central, once rivals that each carried millions of passengers annually, merged in 1968 out of desperation. 2 years later, the merged Penn Central declared bankruptcy, at the time, the largest corporate bankruptcy in American history. By 1970, American passenger rail service had deteriorated to the point where some observers thought it might disappear entirely. Congress faced a choice: let passenger rail die or intervene. They chose intervention. On May 1, 1971, the National Railroad Passenger Corporation began operations. You know it better as Amtrak. It was a compromise solution, a for-profit corporation owned by the federal government, taking over the passenger services that private railroads could no longer afford to operate. But while America was managing this decline, something remarkable was happening elsewhere. In 1964, just as American passenger rail was beginning its steepest decline, Japan opened the Tokaido Shinkansen between Tokyo and Osaka, the first purpose-built high-speed rail line in the world. It operated at 130 miles per hour initially, later increased to 155 miles per hour. It was a sensation, demonstrating that trains could compete with airlines even in the jet age. France followed with its TGV, Train à Grande Vitesse, opening its first high-speed line in 1981. The TGV Paris-Lyon operated at 168 miles per hour in regular service and broke speed records that captured the world's imagination. Germany developed the IC, Italy the Frecciarossa. By the 1990s, high-speed rail networks were expanding across Europe and Asia. America watched from the sidelines. Amtrak, chronically underfunded and operating on aging infrastructure, struggled just to maintain existing service. The idea of building dedicated high-speed rail seemed like a fantasy. But in one corridor, the densely populated stretch between Boston, New York, Philadelphia, and Washington, there was hope. The Northeast Corridor was Amtrak's one profitable route, accounting for more than half its ridership. If high-speed rail could work anywhere in America, it would be here. The question was, how do you build a high-speed rail system in a country that had spent the last 30 years letting its railroad infrastructure decay? The birth of Acela, America's first HSR attempt. By the early 1990s, political will for high-speed rail began to crystallize. The Clinton administration, elected in 1992, saw investment in passenger rail as part of a broader infrastructure modernization program. Congress authorized funding for what would become Amtrak's most ambitious project, a true high-speed train for the Northeast Corridor. But this wasn't going to be like building the Shinkansen or the TGV. Those systems had one enormous advantage. They were built on entirely new, dedicated rights-of-way. The tracks were engineered specifically for high-speed operation, with gentle curves, grade separation, and no level crossings. Japan and France could design their systems from scratch. Amtrak had no such luxury. The Northeast Corridor was already there, 457 miles of track with a history stretching back to the 1830s. Some sections dated to the very dawn of American railroading. The route passed through some of the most densely developed real estate in the nation. Building an entirely new right-of-way would cost hundreds of billions of dollars and require condemning property through some of America's most expensive cities. It was politically and financially impossible. So, Amtrak had to work with what existed, and what existed was infrastructure designed for a different era. The Northeast Corridor had curves that were too tight for very high speeds. It had ancient bridges and tunnels that couldn't be easily modified. Perhaps most problematically, much of it was shared with freight railroads and commuter services. The tracks between New York and Washington saw not just Amtrak trains, but also freight traffic and multiple commuter rail systems. The solution came from Europe, specifically from tilting train technology. In curves, trains must slow down to prevent passengers from being thrown sideways by centrifugal force. But if the train body itself could tilt into curves, like a motorcycle leaning into a turn, it could maintain higher speeds on existing track. Italy's Pendolino trains had proven the concept. Sweden's X2000 refined it. This would be the key to making high-speed rail work on America's vintage infrastructure. In 1996, Amtrak awarded a contract to a consortium led by Bombardier Transportation and Alstom. The design would be based on the TGV, but heavily modified for American requirements. The train would be electric, drawing power from overhead catenary wires. It would have tilting capability to handle the Northeast Corridor's curves. And critically, it would be built to meet Federal Railroad Administration safety standards, which were significantly more stringent than European regulations. Those FRA regulations created one of the Acela's defining characteristics: its weight. European high-speed trains are relatively lightweight, relying on sophisticated crash energy management. But FRA regulations, written decades earlier based on freight railroad standards, required substantially more structural strength. The result was that Acela trains would be considerably heavier than their European counterparts. Each power car weighed 101 tons, compared to 68 tons for a TGV power car. This weight would have consequences for performance, but it was the price of operating on a shared network with freight trains and older equipment. The design that emerged was striking. The nose of the power car was sculpted for aerodynamics, giving Acela its distinctive appearance. The train sets would be fixed consists, power cars at each end with passenger cars permanently coupled between them. Each train would seat 304 passengers in a mix of business class and first-class accommodations. Inside, Amtrak specified amenities designed to compete with airline shuttles: leather seats, electrical outlets at every seat, a cafe car, and eventually Wi-Fi. This wasn't just a train, it was a mobile office for the business travelers who were the target market. The tilting mechanism was sophisticated. In curves, the train body would tilt up to 4 degrees, allowing it to maintain speeds up to 40% faster than conventional trains on the same track. Accelerometers and gyroscopes would measure the forces in real time, adjusting the tilt continuously. Testing began in late 1999. The trains proved the technology worked, but also revealed problems. Cracks appeared in the yaw dampers, components that prevent side-to-side oscillation. There were issues with the braking systems. The testing program stretched longer than anticipated. Finally, on December 11, 2000, Acela Express entered revenue service. The first train departed Washington Union Station bound for Boston, carrying passengers who had paid premium fares for the promise of high-speed travel. The journey time between New York and Washington was cut to 2 hours and 45 minutes. Boston to New York would take just 3.5 hours. The name itself, Acela, was a creation of marketing consultants meant to evoke acceleration and excellence. Not everyone loved it. Railroad enthusiasts and some employees grumbled about the invented word, preferring traditional railroad naming conventions. But Amtrak was betting on a new image, one that broke from the past. What Amtrak had created was something uniquely American. Not quite a true high-speed train by international standards, but the fastest passenger rail service in the Western Hemisphere. It was a compromise between ambition and reality, between what American passenger rail wanted to be and what the infrastructure would allow it to become, the Acela era. Reality versus expectation. When Acela entered service at the end of 2000, the expectations were enormous. Here, finally, was America's answer to the bullet trains of Japan and Europe. Amtrak's marketing emphasized speed and modernity. Business travelers, the target demographic, were promised a competitive alternative to flying or driving. But within the first year of operation, the reality became clear. Acela was fast, but not that fast. The maximum authorized speed was 150 miles per hour, and this could only be achieved on 2 relatively short sections of track. One stretch in Rhode Island, another in Massachusetts. Combined, these high-speed segments totaled less than 50 miles out of the entire 457-mile northeast corridor. For the vast majority of its journey, Acela was constrained by the same factors that limited every other train on the route. Curves designed for 19th century operations, bottlenecks through Baltimore and Maryland, the ancient tunnels approaching New York, and speed restrictions through populated areas. The average speed between Washington and Boston, including stops, was just 82 miles per hour. Point to point, from New York to Washington, about 80 miles per hour. These were improvements over the previous Metroliner service, certainly. But compare this to the TGV, with average speeds over 170 miles per hour on its purpose-built lines, or the Shinkansen's average of 165 miles per hour. By international high-speed rail standards, Acela was barely breaking into the category. Yet in the context of American passenger rail, Acela was a phenomenon. Business travelers embraced it. The trains ran full, especially during the critical Monday morning and Friday evening peak periods. For travel between New York and Washington, Acela captured significant market share from the airlines. The cafe car, the leather seats, the ability to work throughout the journey, these amenities resonated with passengers. Amtrak found its niche. Rather than trying to compete on pure speed, Acela positioned itself as a premium experience. First-class service included complimentary meals and beverages. Business class offered substantially more space than airline coach. And crucially, Acela delivered passengers from city center to city center. No security lines, no drives to suburban airports, no connection hassles. The route itself imposed constant constraints. Consider the approaches to New York City. Trains from the south must navigate through Baltimore, where the route threads between freight yards and requires crossing the Susquehanna River on bridges built in 1906. Then comes the most significant bottleneck. The Baltimore and Potomac Tunnel, a pair of single-track tunnels built in 1873. The bore is so tight that clearances are measured in inches. Speed limit? 30 miles per hour. North of New York, the situation isn't much better. The route follows the shoreline through Connecticut, a stretch with so many curves that sustained high speeds are impossible. There are over 200 bridges in Connecticut alone, many dating to the early 20th century. Then comes the problem of ownership. Amtrak owns its infrastructure in the Northeast Corridor, but commuter agencies operate over the same tracks. Metro North uses the route in Connecticut and New York. The MBTA operates on the tracks around Boston. Schedules must be coordinated. Maintenance windows are precious and limited. The physical plant itself requires constant attention. The overhead catenary system that powers Acela uses two different voltages, 12 kilovolt, 25 Hz AC south of New York, and 25 kilovolt, 60 Hz AC north of New Haven. This necessitated dual voltage capability in the locomotives, adding complexity and weight. The constant current collection at high speeds creates wear on both the pantographs and the wire, requiring intensive maintenance. Then there are the restrictions that exist nowhere else in the high-speed rail world. Federal Railroad Administration regulations required Acela to meet buff strength standards designed for freight railroad collisions. The trains had to be able to withstand 800,000 pounds of force in a collision, far beyond what any European regulation required. This drove the heavy construction that limited acceleration and top speed. Operating rules added further constraints. Many sections of the Northeast Corridor still use signal systems designed in the early 20th century. Cab signaling provides some speed increases, but there are still locations where engineers must operate on visual signals alone. Weather restrictions sometimes required speed reductions. Freight train interference, while less common on the Northeast Corridor than elsewhere, still occasionally delayed Acela services. Despite all these limitations, Acela succeeded commercially. By the mid-2000s, it carried over 3 million passengers annually. Revenue from the Northeast Corridor, primarily Acela and the regional trains, subsidized Amtrak's money-losing long-distance routes. The trains became a familiar sight, their distinctive nose profile marking them as something different from the ordinary Amfleet coaches of the regional service. The passenger experience evolved over the years. Wi-Fi was added, though the signal quality varied depending on location. The food service went through multiple iterations, as Amtrak tried to balance cost and quality. The interiors, originally designed to feel modern and businesslike, began to show wear from heavy use. But the fundamental promise remained unfulfilled. Acela had proven that Americans would ride trains if they offered the right combination of speed, frequency, and amenities. It had proven that passenger rail could be financially viable in the right markets. What it hadn't proven was that America could build true high-speed rail competitive with the best systems in the world. The question that lingered, that rail advocates and transportation planners kept asking, was simple. If this is what could be done with upgraded conventional infrastructure, what might be possible with purpose-built, high-speed lines? Why Acela isn't truly high-speed? The international definition of high-speed rail is generally accepted as 155 miles per hour or faster on upgraded track, or 186 miles per hour or faster on purpose-built lines. By the stricter definition, Acela doesn't quite qualify. By the more lenient one, it barely makes the cut. But beyond the technical definitions, there's a more fundamental question. Why can't Acela go 200 miles per hour like the TGV or Shinkansen? The answer lies in the physics of railroad engineering, compounded by decades of deferred investment and regulatory frameworks designed for a different era. Start with the most basic constraint, curve radius. When a train goes around a curve at high speed, passengers experience centrifugal force pushing them outward. The faster the speed, the greater the force. To maintain passenger comfort, there's a maximum speed for any given curve radius. The tighter the curve, the slower the train must go. European and Asian high-speed lines are engineered with curve radii measured in thousands of meters. The TGV lines typically have minimum curve radii of 4,000 meters. The Shinkansen uses curves of 2,500 meters or greater on its oldest lines, and up to 4,000 meters on newer routes. These gentle curves allow sustained speeds of 200 miles per hour or more. The Northeast Corridor, by contrast, has curves as tight as 200 meters in some locations. Even with Acela's tilting capability, which effectively increases the allowable speed in curves, these radii fundamentally limit how fast the train can go. You can't engineer around geometry. A curve is a curve, and there's only so much speed it can accommodate. Then there's the infrastructure itself. High-speed rail requires incredibly precise track geometry. The rails must be held in position with tolerances measured in millimeters. Any deviation creates oscillation and vibration that limits speed. Purpose-built high-speed lines use continuously welded rail on concrete slab track, creating a stable platform that allows sustained high speeds. Much of the Northeast Corridor uses ballasted track, crushed stone, supporting wooden or concrete ties. This is more forgiving and easier to maintain, but it's also less stable at very high speeds. The constant pounding of trains, combined with weather effects, creates settlement and geometric deviations that require regular maintenance and impose speed restrictions. The regulatory environment adds another layer of complexity. The Federal Railroad Administration's regulations were written with freight railroad safety in mind, emphasizing crashworthiness through structural strength. European regulations take a different approach, using crash energy management. The train structure deforms in controlled ways to absorb collision forces, protecting the passenger compartment. The result is that Acela trains are roughly 30% heavier than comparable European high-speed trains. This weight affects everything. Heavier trains require more power to accelerate. They take longer to reach top speed and longer to brake. They impose greater forces on the track, increasing maintenance requirements. The power-to-weight ratio that allows a TGV to accelerate briskly is simply not achievable with Acela's FRA-compliant construction. There's also the matter of dedicated infrastructure. The Shinkansen operates on tracks used exclusively for high-speed passenger service. No freight trains, no slower commuter trains, no conflicts. This allows for optimized scheduling and maintenance windows. The TGV has similarly dedicated lines for most of its routes. Acela shares its tracks. Freight trains, while not common on the Northeast Corridor, still operate on parts of the route. Commuter trains run constantly, especially near major cities. This mixed traffic means Acela can never be scheduled for optimal speed. It's always working around other services. The political dimension cannot be ignored. Building dedicated high-speed rail requires enormous capital investment, sustained over decades. It requires federal, state, and local cooperation. It requires the political will to commit billions of dollars to infrastructure that won't show returns for years. Japan made that commitment in the 1960s. France made it in the 1970s. Spain, seeing the success of its neighbors, made it in the 1990s and built one of the world's most extensive high-speed rail networks in just 2 decades. China began building high-speed rail in the 2000s and now operates more high-speed track than the rest of the world combined. America has struggled to make that commitment. Funding for Amtrak in the Northeast Corridor has been inconsistent, subject to political winds. Major infrastructure projects face environmental reviews, property acquisition challenges, and local opposition. The Hudson River tunnels between New Jersey and New York, critical bottlenecks, have been identified as needing replacement for decades, but funding and planning have been mired in political disputes. There's also the cultural factor. Americans embrace cars in a way that makes passenger rail a harder sell. The federal government has spent trillions on highway infrastructure over the past 70 years. Airports receive substantial federal support. But passenger rail has never commanded the same sustained political commitment. Acela operates within all these constraints: physical, regulatory, financial, and political. It's a train designed to be as fast as possible on infrastructure that wasn't built for speed, operating under regulations written for freight railroads, funded by budgets that reflect political ambivalence about passenger rail. The miracle isn't that Acela isn't faster. The miracle is that it exists at all, and that it works as well as it does. But for a nation that once led the world in railroad technology, that built the first transcontinental railroad and pioneered diesel-electric locomotives, it's a reminder of how far American passenger rail has fallen and how far it still has to climb. The future, Acela II, and America's new hope. By the 2010s, the original Acela train sets were showing their age. Built in the late 1990s, they had been in continuous heavy service for over a decade. More importantly, train technology had advanced. Newer designs offered better performance, lower maintenance costs, and improved passenger amenities. Amtrak began planning for the next generation. In 2016, Amtrak placed an order with Alstom for 28 new high-speed train sets, designated the Acela Liberty. These trains represent the evolution of everything, learned from 2 decades of Acela operation. They are based on Alstom's Acela platform, which has proven successful in European service, but customized for American requirements and infrastructure. The Acela Liberty train sets are longer than the original Acela, 9 passenger cars instead of 6, with seating for 386 passengers versus 304. They're also lighter, using modern materials and construction techniques that reduce weight while maintaining FRA-mandated structural strength. The power cars produce 13,600 horsepower combined, substantially more than the original Acela's 12,000 horsepower. Despite being longer and carrying more passengers, the new trains have a better power-to-weight ratio. The maximum speed increases to 160 miles per hour. Not a revolutionary jump from Acela's 150, but every bit counts. More importantly, the improved acceleration means the trains reach top speed faster and maintain it more efficiently. The tilting mechanism has been refined, using technology proven on Alstom's Pendolino designs in Italy and the UK. The tilt system is fully active, continuously adjusting to track conditions in real time. Inside, the design reflects modern expectations. Each seat has access to power outlets and USB ports. The Wi-Fi system is integrated into the train's design rather than retrofitted. The lighting uses LEDs, creating a more pleasant ambiance while reducing energy consumption. The cafe car has been reimagined with more preparation space and better equipment. Accessibility features have been enhanced throughout. But the introduction of the Acela Liberty has been anything but smooth. Originally scheduled to enter service in 2021, the trains faced repeated delays. Testing revealed issues that required modifications. FRA certification took longer than expected. Infrastructure improvements needed to accommodate the longer trains fell behind schedule. As of 2024, the trains are still undergoing testing and modification, with revenue service now expected in the mid-2020s. These delays are frustrating, but not surprising. Introducing new rolling stock always presents challenges. When that rolling stock must meet uniquely stringent American regulations and operate on complex shared infrastructure, the challenges multiply. Amtrak and Alstom are methodically working through each issue, but the process takes time. Meanwhile, other high-speed rail projects are emerging across America, some advancing, others stalled, all reflecting the complicated politics and economics of passenger rail in the United States. In California, the California High-Speed Rail Project represents the most ambitious attempt to build true high-speed rail in America. The full project would connect San Francisco to Los Angeles, with trains operating at up to 220 miles per hour on dedicated tracks. The initial segment under construction in the Central Valley will be the first purpose-built high-speed rail line in the United States. But the project has been plagued by cost overruns, schedule delays, and political controversy. Initial cost estimates of $33 billion have risen to over $100 billion for the full system. Construction that was supposed to be completed by 2020 continues with no clear end date. The project's future remains uncertain, dependent on continued state funding and political support. In Texas, Texas Central partnered with JR Central of Japan to bring Shinkansen technology to America. The proposed line between Dallas and Houston would use N700S train sets, the same technology operating in Japan today, on entirely new, dedicated infrastructure. But the project has faced legal challenges from landowners, funding difficulties, and regulatory hurdles. Progress has stalled, and the project's fate is unclear. More successful is Brightline, a privately funded higher-speed rail service in Florida. Operating between Miami, Fort Lauderdale, and West Palm Beach since 2018, Brightline extended to Orlando in 2023. The trains reach 125 miles per hour on some sections, not quite high-speed rail by international standards, but faster than most American passenger trains. Perhaps more importantly, Brightline has proven that private investment in passenger rail can work in the right markets. Brightline is now developing Brightline West, a true high-speed line that will connect Las Vegas to Southern California. This project has federal support and has cleared major regulatory hurdles. If completed, it would be the first purpose-built high-speed rail line in America to reach international speed standards, with trains operating at 200 miles per hour. Back on the Northeast Corridor, beyond the new train sets, larger infrastructure improvements are critical. The Gateway program aims to build new tunnels under the Hudson River and expand Penn Station, New York. These tunnels are essential. The existing tubes built in 1910 are deteriorating and were damaged by Hurricane Sandy. Without them, Acela and all Northeast Corridor service faces an existential threat. The Baltimore and Potomac Tunnel Replacement Project would eliminate one of the Northeast Corridor's worst bottlenecks. The new tunnel would allow speeds of 100 miles per hour compared to the current 30, cutting minutes from journey times and improving reliability. The Susquehanna River Bridge replacement would similarly upgrade one of the corridor's oldest structures. The Connecticut High-Speed Rail Project proposes straightening curves and upgrading infrastructure through one of the route's most constrained sections. Each of these projects is in various stages of planning, funding, and construction. Each faces the familiar challenges: cost, politics, regulatory complexity. But together, they represent recognition that incremental improvements, while not as dramatic as purpose-built high-speed lines, can meaningfully improve performance on the infrastructure that exists. The vision for American high-speed rail in 2025 is simultaneously hopeful and frustrating. Technology exists to build world-class systems. The potential demand is clear in regions like the Northeast Corridor, California, Texas, and the Midwest. But the political and financial commitment remains inconsistent. What the Acela Liberty represents, then, is a bridge between the compromise of the original Acela and the potential of true high-speed rail. It's faster, more efficient, more comfortable, but it still operates on tracks designed for a previous century, constrained by the same fundamental limitations that have always defined American passenger rail: the American HSR dream. The story of Acela is, in many ways, the story of American passenger rail itself: ambitious, compromised, persistent, and ultimately defined as much by what it couldn't be as by what it achieved. When Acela entered service in December 2000, it represented a bet that Americans would ride trains if those trains were fast enough, comfortable enough, convenient enough. That bet paid off. Acela proved that there was a market for premium passenger rail service, that business travelers would choose trains over planes when the experience was right. It demonstrated that modern, relatively fast trains could compete in the densely populated Northeast megalopolis. But Acela also exposed the depth of the challenge facing American high-speed rail. It revealed that you can't simply drop European or Japanese technology onto American infrastructure and expect world-class results. The tracks matter, the regulatory environment matters, the sustained investment matters, and most of all, the political commitment to passenger rail matters. Look at the trajectory of passenger rail in other countries, and you see consistent patterns. Japan decided in the 1960s that high-speed rail was a national priority and built accordingly. France made the same decision in the 1970s and constructed one of the world's premier systems. Spain, seeing the success of its neighbors, committed billions in the 1990s and early 2000s, building a network that now rivals France's in extent. China, starting from almost nothing in the early 2000s, built the world's largest high-speed rail network in less than 2 decades through massive state investment. In each case, the commitment was sustained across changes in government. The planning horizon was measured in decades. The funding, while sometimes controversial, was ultimately forthcoming. And the result was infrastructure that transformed how people traveled. America has never made that commitment. Funding for Amtrak has been inconsistent. Subject to annual political battles, major infrastructure projects face years of planning and environmental review, then struggle to find funding. High-speed rail proposals are announced with fanfare, then fade as costs rise and political support wanes. The original Acela train sets, now being retired after more than 2 decades of service, operated on infrastructure that, in many places, was older than the trains by a century. The new Acela Liberty trains will face the same constraints: curves too tight, bridges too old, tunnels too narrow, shared tracks limiting optimal scheduling. Yet there is progress. The gateway tunnels under the Hudson will eventually be built. They must be, because the alternatives are unthinkable. The Baltimore Tunnel will be replaced. Infrastructure along the Northeast Corridor continues to improve incrementally. And beyond the Northeast, projects like Brightline West and segments of California high-speed rail represent genuine attempts to build modern, purpose-designed high-speed lines. The technology has never been the barrier. American engineers helped develop the electric locomotives that enabled high-speed rail. American manufacturers have built components for high-speed trains worldwide. The expertise exists. What has been missing is the sustained political and financial commitment that high-speed rail requires. Acela occupies a unique place in that context. It's not the high-speed rail system that advocates dreamed of. It's not competitive with the best systems in Europe and Asia. Its average speeds are modest by international standards, constrained by infrastructure that limits its potential. But Acela is real. It exists. It carries millions of passengers every year. It generates revenue. It proves that Americans will ride trains when the service meets their needs. And perhaps most importantly, it keeps alive the idea that better is possible. The new Avelia Liberty trains, when they finally enter service, will be incrementally better, faster, more comfortable, more efficient. They won't transform American passenger rail, but they'll improve it. An improvement, in the context of American passenger rail, is worth celebrating. The dream of true high-speed rail in America, trains running at 200 miles per hour on purpose-built tracks, connecting major cities with journey times competitive with flying, remains alive. California's Central Valley segment edges toward completion. Brightline West advances toward construction. And in the Northeast, the slow work of upgrading century-old infrastructure continues. Perhaps one day there will be a train that truly earns the title of America's bullet train. A train that reaches 200 miles per hour as a matter of routine, not just on short test segments. A train operating on infrastructure designed for speed from the beginning, not adapted from the 19th century. A train that can compete with the best high-speed rail systems in the world. Until that day comes, we have Acela, imperfect, compromised, but persistently connecting Boston, New York, and Washington at the fastest speeds American infrastructure will allow. It's not the bullet train that America could have built, but it's the bullet train that America did build. And for millions of passengers, that's enough to keep the dream of high-speed rail alive. The story of America's bullet train isn't finished. In many ways, it's only beginning.